Hello viewers, myself Dr. Mahantesh K, Department of EC SJBIT, Bangalore. Welcome you to this online video sessions on electromagnetic waves prescribed by BTU, Module 2, Class 11. In this video, we are going to learn about the concepts like divergence, which is the continuation of your previous video concept topic called distributed distribution of charges and uniform volume. So we shall now obtain an exact relationship by allowing the volume element delta V shrinking to zero just in order to obtain the constant charge distribution or density. So as we know from our previous discussion, divergence theorem dou dx over dou x plus dou dy over dou y plus dou dz over dz is equal to surface integral dds over delta V, which is equal to q over delta V. So as I've obtained, if we say volume tend to 0, then dou dx over delta x plus dou dy over dou y plus dou dz over dou z will be equal to limit delta V tends to 0 surface integral dds over delta V, which is equal to limits delta V tends to 0 q over delta V. The last term in this equation is the volume charge density, that is rho V, so that I can equate the entire equation of divergence to rho V. But what is rho V equal to? Now let us consider one information that can be obtained from the last equation is rho V. Rho V is nothing but a volume charge density. This equation is valid not only for electric flux density but also to any vector field A. To find the surface integral of a small closed surface, you can equate it to a volume integral of that small closed surface. The operation received a descriptive name called divergence. So what do you mean by a divergence? Divergence of any given vector is equal to surface integral of A dot ds over delta V, where volume tends to 0, which is under the limits delta V tends to 0. The divergence of the vector flux density is the outflow of a flux from a small closed surface per unit volume as the volume shrinks to 0. A positive divergence of a vector quantity indicates a source of that vector quantity at that point, whereas a negative indicates a sink or a convergence of a vector to that point. Now, from the derivation, we can understand the divergence in rectangular coordinate system, that is divergence of d equal to dou dx over dou x plus dou dy over dou y plus dou dz over dou z. Whereas in cylindrical coordinate system, divergence of d is given by 1 over rho dou by dou rho into rho d rho plus 1 over rho dou d phi over dou phi plus dou dz over dou z. Whereas in cylindrical coordinate system, when compared to rectangular, it is moderately complex. But whereas in spherical coordinate system, there are the involvement of sine theta angles in terms of rho, phi and theta. So divergence of d is given by 1 over r square dou by dou r square dr plus 1 over r sine theta dou by dou theta sine theta d theta plus 1 over r sine theta dou phi by dou phi. Now let us just take an example to apply divergence concept to a given problem. D is given by e power minus x sine by ax minus e power minus ax cos y in the direction ay plus 2z az. Find divergence of d at the origin at point p1, 2, 3. So divergence of d is given by dou dx over dou x plus dou dy over dou y plus dou dz over dou z, which is equal to e power minus x sine y plus e power minus x sine y plus 2. Which is equal to regardless of the location of the divergence of D is equal to 2 coulombs per meter square. We may now rewrite the expressions developed so far from the previous concepts in this video, like divergence of D is equal to surface integral dou ds over delta V while limit delta V tends to 0. Again, we know divergence of D is equal to dou dx over dou x plus dou dy over dou y plus dou dz over dou z. But also divergence of D is equal to rho V using Maxwell's first equation, point form of Gauss law. So this is the Maxwell first equation, that is point form of Gauss law, where delta V tends to 0. It appears to be as a point, and you're trying to evaluate or you're trying to get the divergence of any given point in a vector form. So the first of Maxwell's four equation applies to electrostatics and steady magnetic field both. Physically, it states that the electric flux per unit volume leaving a vanishingly small volume unit is exactly equal to the volume charge density there at that particular point. Now, well, let us just try to understand the vector operator del and the divergence theorem. Divergence is an operation on a vector yielding a scalar, just like the dot product. We define the del operator as del is equal to dou by dou x in the direction ax plus dou by dou y in the direction ay plus dou by dou z in the direction az. Then, treating the del operators as an ordinary vector, we can write del dot d is equal to dou by dou x ax plus dou by dou y ay plus dou by dou z az dot dx ax plus dy ay plus dz az. So here d are some constants in different directions of flux density. Therefore, divergence of D is given by dou dx plus dou dy plus dou dz. These are partial derivatives of flux densities in x, y, z directions. Therefore, divergence of D is given by del dot D, which is equal to the partial derivatives of flux densities in all the directions in Cartesian coordinate system. Now, the del operator does not have a specific form in other coordinate system than rectangular coordinate system. So del dot D in cylindrical coordinate system is given by 1 over rho D by D rho into rho D rho plus 1 over rho dou D phi by dou phi plus dou dz by dou z. Whereas in spherical coordinate system, as given by this equation, it is more similar to your previous equations what we have studied with respect to the divergence theorem. We shall now give the name to that theorem that we actually have obtained so far in the previous slides, that is divergence theorem. Dou ds surface integral of dds is equal to q, which is equal to volume integral of rho v into dv, which is equal to volume integral of d dot del dot d dv. Why? Because rho v is equal to del dot d. Therefore, we can write surface integral of dds is equal to the volume integral of divergence of flux density with respect to the volume. So the integral of the normal component of any vector field over a closed surface is equal to the integral of the divergence of that particular vector field throughout the volume enclosed by that closed surface. So this is the pictorial representation here. So whatever flux density, that is whatever the flux density inside the closed surface will be equal to the divergence of the flux within inside that volume. Example, now evaluate both sides of the divergence theorem for the field given D in coulombs per meter square and rectangular parallel pipette formed by planes x equal to 0 and y is equal to 0 and z is equal to 0 to 3 planes. So divergence theorem states that closed surface integral dds is equal to volume integral of divergence of d into dv. Substituting the values of the given data into the left hand side of the equation and to the right hand side of the equation, we will obtain both the equations in the left hand side and the right hand side will obtain the value of 12 coulomb. So that was the equation with respect to the left hand side, and you obtain 12 coulombs. And with respect to the right hand side, that is divergence of D, and then volume integral of divergence of D gives us 12 coulomb. Hence LHS is equal to RHS. Hence we have proved the divergence theorem. That means surface integral of any closed surface integral of any given vector is equal to the divergence of that vector under that particular volume. Thank you for watching this video. Hope you understood the concepts of divergence in its vector form, divergence theorem, and how we are going to convert it into how we are going to convert surface integral of any given vector into a volume integral of divergence of that vector using divergence theorem along with a simple numerical. Thank you for watching this video. Take care.